This is the third part of levers, pulleys, inclined planes, torque, and angular momentum. We've covered a number of things, but now let's cover basically wheel and axle, which is in a sense a type of lever. So let's assume we had a shaft here and we had a great big wheel. And let's assume that it had a capital radius R. And then let's assume we have a little wheel and it has a capital radius of little r. That would be the radius of the wheel. Suppose we put a force here and we try to spin this around by putting some kind of force here. What force will appear here at this end? And the way to solve this is just to equate the torques again. Once again, the torques of 1 equal the torques of 2. So what is the torque of 1? It's just the big force times the radius of this wheel. What is the torque of the other one? Well, it's the little radius times the force that's produced here. And we'll put a little f. And this looks a lot like the lever equation where we take the force times the distance, which is r, and we take the force times the distance, which in this case is r. And that's all we have to do to calculate what's happening. Let's look at a sample problem. Suppose we have a large wheel here, and attached to it by some pin or something in the center is a small wheel. Let's let the radius of the big wheel be 2 meters. So we'll call this R1, and that will be this distance here. The radius is 2 meters. Let's apply a force of F1 equal 100 newtons to the big wheel. Now the little wheel is tied to it, and let's say that the radius of the little wheel is half a meter. What force will appear here at the little wheel? In order to solve this, we just equate the torques. The torque at 1 is equal to the torque at 2. What is the torque at 1? It is the force at 1 times the radius at 1, the distance to the pivot point. Just like in the lever, it's the distance from the force to the pivot point. In the case of the lever, there's a fulcrum here. In the case of a wheel, there is a pin or something, a shaft in the center, and it's this distance that we're looking for, this radius. That has to equal F2, I don't know what that is yet, times the radius of this wheel that it's turning. And so this was going to be R2. To solve for F2, I have F1 times R1 divided by R2. And this turns out to be 100 newtons times 2 meters divided by 0.5 meters. The meters cancel out, and we are left with an answer of 400 newtons. So if we apply 100 newtons to the top of this wheel, to the big wheel, then that will produce a force of 400 newtons on the little wheel. How does that work? Well, the 100 newtons is applied here at the top. That's the 100 newtons. But if I turn it all the way around, it has to go this entire distance. That is with a force of 100 newtons. It is true that it will produce at the little wheel 400 newtons, but I only get that for a little distance around this wheel. So once again, I trade force for distance, just as we did in the lever. Now let's talk about a system of pulleys. Many machines have a system of pulleys that in some form or another, but let's look at it this way. Suppose I extend a pulley from the ceiling and run a rope over it and let you stand here and pull on the rope, and you pull up a weight, and let's say the weight is 100 newtons. You will have to pull down with the same force of 100 newtons. Now, almost always there's friction in the pulley, but we're going to ignore all the friction and just look at the other mechanics of the problem. You have to pull 100 newtons to get this to go up 100 newtons. If you pull this down a distance of a meter, this will go up a distance of a meter. So the mechanical advantage of this one pulley is simply one. The force in is 100 newtons. The force out is 100 newtons. And we get a mechanical advantage of 1. Now let's try something a little bit different. Suppose we have a wall here, or a ceiling, a type of a barrier of some kind holding it up, and suppose we simply attach a rope to that, and we let the rope hang down and let you stand right here, and you're going to pull up on the rope. We'll attach a pulley at the bottom of the rope, and the weight hangs from the pulley. So let's once again put 100 newtons here. Now think about what you're doing as you're pulling this rope up and down. The rope is tied here, so clearly it's not going to move from here. What is going to happen is you're going to pull it up, and the little wheel here, the pulley, will come up with it, and the rope will slide around it, frictionless in our case, and you'll pull it up. Well, with what force do you have to pull it? Well, think about it. If you simply tie your rope off right here and don't pull it all, you can hold up the 100 newtons by simply having half of the force here. This rope pulls up with 50 newtons, and you pull up with 50 newtons, and that's a total of 100 newtons. But to get this to move, to get the block, the weight to move 1 meter, you have to pull 2 meters of rope, because part of that rope comes from the other side and part of it comes from your side. So what you find is, as is always the case, we're assuming no friction here and no work is lost, that the work in is equal to the work out. So that the force you apply times the distance you apply it over is equal to the force of the input times that distance. And we'll make this the inside and this the outward side. So we see that in this case our pulley has a mechanical advantage of 2 because we only have to pull up with a force of 50 newtons to pull up the 100 Newton block. Why? Because the rope over here is holding up part of the weight itself. So now it turns out that pulley systems are easy. If you have a weight hanging, let's say, from the center of this pulley, all you have to do is count the number of supporting ropes to the weight. So let's suppose that we tie a rope right here, and we run it over another pulley, and we bring it down to our hand. How many ropes actually support the weight? Well, only this one right here, because imagine in your mind that each of the rope is tied at the pulley. So that rope is tied. This rope that you're holding in your hand does not actually connect to the weight. So think about it in these terms. So only 2 sections of the rope, this section coming up here, supports the weight. So in this case, what we find is that you will have to pull down equal to the weight. But let's start using some numbers, and so we'll say 100 newtons is the weight. You would have to pull down with 100 newtons because there's only this rope right here that's actually supporting the weight. Again, to help you understand this and solve the problem, you can imagine that the ropes are tied at the contact point. But now let's try another case. Suppose we have here a pulley, and again, let's tie our weight, our load, whatever, weight down to this. Here we stand here with a pulley, and let's run the pulley here up, over this one, back around this one, and now let's tie it to the bottom pulley. How many ropes are supporting the pulley? Well, this rope segment, how many rope segments is a better way to look at it maybe. This rope segment is supporting the pulley, so that's 1. This rope segment here is supporting the weight, so that's 2. This one right here, that's 2. So go back, this is 1. This is 2. This rope segment from here up to here is supporting the load, so that's number 3. And now we're left with this rope segment here, but it's not supporting the load. It simply would be attached, in a sense, at least conceptually, to the pulley right here. So we have 1, 2, 3 ropes that are holding the weight. So what load do we have to pull with? What force do we pull with? We would pull then with 1/3 of the weight, because there are 1, 2, 3 pulleys supporting the weight. Okay, let's try one more problem. Let's tie a rope here, right in the center of this pulley. Let's have a weight hanging from it. We have a pulley in the ceiling. Let's run the rope over the top pulley. Let's let it come around and wrap around that pulley. Let's let it come around, because this would be like a double pulley, so you have little tracks for this to run on. Come around to this, come around again. We would put a triple track up here on this pulley, and then we would come over here, and now you're pulling on this. With what force do you have to pull down to say this is 100 newtons? What force would you have to pull down with? How do we solve this? Once again, we count the number of supporting ropes. This rope is not supporting the weight, because we consider each rope segment is tied at the pulley. So that one is not supporting it, but we have 1, 2, 3, 4, 5 rope segments, if we count them each tied off, that are supporting the weight. So how much do you have to lift with? 100 newtons divided by the 5 supporting ropes, you would lift with a force of 20 newtons. But nothing is free. So how is it you're able to lift with only 20 newtons at this end and pull up 100 newtons this way? Well, remember, the work in is going to be equal to the work out, and we're assuming this is frictionless and there's no friction in here. So it's true that you pull with only 20 newtons. But the work in is going to be that 20 newtons times the distance you have to pull it, right? And that's going to be equal to 100 newtons times the distance this moves. We'll call this D1 and D2. So we can see very quickly if these two are equal to each other, if they're equal to each other, then we do pull with 20 newtons here, but we have to pull 5 times as much rope in order to get the weight to come up. So the weight will move 1 meter, and we'll pull out 5 meters of rope, so that the work in is always equal to the work out. Our final item here that we want to discuss, and this closes our little sessions, is the idea of angular momentum. When you were in pre-AP chemistry, you looked at quantum numbers, and n was the principal quantum number, which was the energy level. And then there was one called L. L is actually the angular momentum, and that word was used, but you might not really have thought or known what it was in class. So think about this. If you had a force this way, and a pivot point here, and you were running this, pivoting around the circle, what would you call this force times this distance? Well, we know that's called the torque. The torque is going to be the force times the distance. So there's a similar concept that if you have something moving in this direction, it has mass and it has velocity, and we call that the momentum, the linear momentum. If we multiply that times the distance, we have what is called the angular momentum, and it's given the symbol L. So the angular momentum is going to be P times this distance D in here. Now it's usually given the symbol R, so it usually looks like mvr. The momentum times the distance that you're moving that momentum through. And this is, angular momentum only occurs for things that are going in some kind of arc. They don't actually have to be circles, but they're not straight lines. So this is the angular momentum. It's the mass times the velocity, which is the momentum you already know, times this perpendicular distance to the pivot point, or the thing that you're rotating around.